All right. Can we hear me now?
Yeah.
Okay. Back to here.
Yep.
Okay, so thank you again for the introduction. As you said, my name is Brandon Jones. I'm from Google, and all the thunder on this slide was just stolen because he went through all of it. I am on the Chrome GPU team. I've contributed to multiple web specs before, mostly around graphics in some capacity. The thing that wasn't mentioned is that I have the distinct privilege of working with multiple alumni of this very class. Austin Eng, Shrek Xiao, Kaini Nomiya, all people who came from this program and work with me now on these very things. They're great people to collaborate with. And I'm so happy that I could be here to represent the team to this class again. So the things that we'll be covering today are just kind of a grab bag of topics in and around WebGPU, why we're developing it, compare it to WebGPU and WebGL, which my understanding is that the class has at least covered WebGL a little bit, so hopefully that won't be too off in the weeds. Why WebGPU is going to be more efficient than WebGL. We'll dive into some of the concepts of the API itself, talk about ways that we aid in debugging, and have just some general tips for if you should find yourself using the API. I'll also note that if anybody wants, all of these slides are available online right now, so you can go grab them. I'll also make sure that that link is available at the end and make sure that it's available to put on the class site. So first, before we dive into WebGPU, I want to talk a little bit about WebGL itself, because this is the first API that I was kind of involved in helping bring up on the web. And WebGL is cool because it effectively gives us ubiquitous real-time 3D graphics everywhere and anywhere. This is an API where any one of you can pull out any device from your backpack or phone, go to a page with WebGL, and it is basically guaranteed to work at this point. WebGL, WebGL2, we can do it on pretty much any modern device. It's on every major browser, every major platform, and that in and of itself makes this really special. And it's not for the reasons that we thought when we were developing WebGL initially. When WebGL was first being developed, we had a lot of expectations that, oh, this is going to be great for games on the web. Especially because at that time, Flash was dying a slow and painful death, and we needed something to come in and take the place of it when rendering things quickly. And so there was a lot of talk about games. And then we released it, and there are games. There are cool WebGL games out there. They're fun, they're great to play, they make their creators money. But that's actually not where we saw the most interesting, the most kind of magical content. What we really saw more of that surprised us as the developers of the API was that suddenly you had the New York Times doing data visualization with WebGL, and Matterport doing real estate walkthroughs with WebGL, and Sketchfab doing artist portfolios with WebGL, and ShaderToy doing whatever the hell it is that ShaderToy does with WebGL. And the cool thing about this is none of those use cases made sense anywhere but the web. Like if you went to NewYorkTimes.com and they said, we have a really cool 3D bar graph to show you. And you're like, cool, show it to me. Click the button. They're like, first, go get this app. Nope, I'm out. I don't care anymore. You've given me too much friction to get to whatever you wanted to show me. But if you go and it's in the article itself and it's already spinning and it's already visible, that is a worthwhile experience. I've now gained something new. I have that richer piece of content available to me. And then when I click the back button, it all goes away. It's ephemeral. And that is a very magical property of the web, and it gives rise to all of these use cases that just don't make sense anywhere else. But WebGL, for all of its coolness, does have some problems. Primarily, it's old, and it's based on older things. WebGL itself is about 11 years old at this point, and the newest version came out in 2017, which was based on an API from 2012. So the newest thing that you can do is already a decade old. The original WebGL came out in 2011. It was based on something from 2007, which is when the iPhone was originally launched. And those APIs themselves are mobile variants of an API that was released in 1993. We're talking 3 decades old now. And a lot of the patterns that were available in this have stuck through all the way up to here. Graphics have evolved slightly in those 30 years. You know, this is from 1993. It was on, I believe, I want to say some of the SGI systems that were available at the time. This was what they used to demonstrate WebGL, or excuse me, OpenGL 1.0 when it came out. And this is what just an average game looks like today. It's ridiculous. Fun fact, the machine that the machine that you needed to run this cost about $250,000 in 1993. This is $500 at Target. So we've come a long way. And native APIs have had to evolve to keep up with that as well. So nowadays, instead of OpenGL and some of the older versions of DirectX, we have Vulkan, which is kind of the successor to OpenGL. We have Direct3D 12, and we have Metal, and all of these are collectively kind of thought of as the modern APIs. They're still a little old at this point, but you know, they have kept up with the latest and greatest hardware demands much better than some of these older systems did. So unfortunately, WebGL just can't keep up with those newer APIs. The APIs that it is based on are basically in maintenance mode. Kronos has said that they're not really going to move forward with those features anymore. And it's based on an API that was never really designed to work on the web. We have shoehorned it onto the web. We have made it work the best it can. It's gotten some really great use out of it, but it was never designed to feel like a native API there. And that's what brings us to WebGPU. So the goal of WebGPU is to expose the capabilities of all these new modern APIs, do so in a way that feels like it's web native. It feels like it belongs on the platform and wasn't just a port of something that came before. Use all of the modern features of the native APIs and the web, and build it with extensibility in mind so that hopefully this can last for the next decade or more. So some of the new features that we do want to bring into it, just a high level, compute shaders, indirect drawing, render bundles, external textures, all of these different things that they're available in Vulkan and whatnot. I'm going to talk a lot about Vulkan because that's the one that I'm most familiar with, but you can kind of broadly extrapolate that out to apply to the other APIs as well. And these are things that on the native side, we've been able to do for years. You go to SIGGRAPH and watch somebody talk about it, and they're like, look at all these cool tricks that you could do. And as a web developer, you go, yay, I'll get to do that in like a decade. But we're taking a significant step up from WebGL. Oh, and because this is a talk about graphics APIs, I would be remiss if I didn't show off at least some pretty pixels. So these projects are ones that I've built as we've been developing the API to kind of test out the features, stretch the limits, find out where the rough spots are, and use for demonstrations like this. They're also open source, so if you want to go and poke at the code that runs these, you can. That was my purpose in building them, is to educate. And so this one is, there's a chair there. This one is basically a really quick demonstration of an algorithm called metaballs, or also marching cubes. It's marching cubes that are triangulating metaballs. And it's just this really simple thing that's been around for a long time, where we've got these bouncing balls that kind of merge into each other. And the interesting thing is not so much the complexity of the little balls themselves, because they're not particularly complex, but how complex it is to triangulate them. So you can see, here's the points that drive that. It's not too particularly intense. We can turn that up a little bit more. Now, this is being done in a compute shader. So all of the triangulation of that and the computation of where the balls are and everything, that's being done on the GPU. And that makes it really efficient to then hand that over for rendering later on. Now, by comparison, if I switch this over and said, I want you to do all the same exact computations in JavaScript on the page, it's going to be a little hard to see here, but you can see we were running at a steady 60 frames per second. Now we're running at 16. I have a higher level that I can go to, and it shows this off even better, where the difference is like 60 frames per second for the GPU and 4 for JavaScript. But that causes a bug in Chrome, and so I'm not going to do it because this is still an API that's under development. The other one I'll show off today is this is something seasonally appropriate that I developed last year. It's just a game. It's Breakout. It's nothing fancy, but I did this specifically just to show that we can put all these pieces together and they do something interesting. And in fact, I'm gonna take 2 seconds to go to a different version of this, kick that off, and then pause it to a free camera, and now we can wander around the scene a little bit. So you can see that some of the basics things that we have here are we have animating characters, they cast shadows, we can do dynamic lights. We've got big shadows coming from this tree over here. There's some bloom on various different things. None of this is particularly complex. It's all techniques that have been around for a little while, but it's been an interesting exercise to put them all together under this new API and see where the rough points are, so we can file them down, making sure that it's an easy API to use. So back over to here now. So in any case, as we're going through all of this, and we're looking at the features that we have available compared to WebGL and everything, one of the questions that might come up is, well, if you had WebGL and OpenGL's successor was Vulkan, why not just do a Web Vulkan? And there's a myriad of reasons for that. I'll give my personal ones, which is I find Vulkan ever so slightly intimidating. It is a large API, a very complex API. And if you're coming from something like OpenGL or WebGL, it feels a little overwhelming. Now that slide was a joke, but it was not an exaggeration. What we have here is somebody went and compiled how much code it takes to draw one triangle with various APIs. WebGL is going to be most closely equivalent to this OpenGL 3 over here. DirectX 12 is probably one of the longer ones here. And then you can see Vulkan. We're not done yet. It is a verbose API. And so we kind of don't want to expose all that to the web. But beyond just the complexity, we have a lot of different considerations that go into making a web API. One of the most basic ones being that the code you write on any given device for the web should have a reasonable expectation that it can work on any other device. If I build something on my MacBook, I should be able to run it on my Windows machine. If I build it on my Linux desktop, it should run on my Android phone. That is very much not the goal of something like Vulkan. In fact, they go out of their way to expose the differences between the platforms so that you can take better advantage of it. That is a valid choice for them and their goals. Like I actually had the privilege of being in the room when a lot of that API was being built, and a lot of it was, hey, we've got Epic and Unreal and well, Epic does Unreal, but we've got the Unreal engine and the Unity people and everybody else in the room. What is going to work best for you? And the answer was, we want to take advantage of every last piece of hardware, no matter the cost. And so that's what those APIs are designed to be good at, and they are good at it. But that's not what the web wants to be good at. We want to make sure that if there are incompatibilities, it's always an opt-in thing. And we need to absolutely make sure that web APIs are safe, period. There is no negotiation on that point. You should never be able to go to a web page and crash your computer. If you do, it is our fault. And it was something that we've done drastically wrong. You should never be able to go to a web page and have it see memory from the next web page 2 tabs over, which might be your bank. That's bad. We have to make sure that these things are well isolated, and that's not a requirement that the native APIs have. So it makes sense for us to design an API that is going to work better within those constraints. This is kind of saying the same thing I just said. Like WebGPU is designed for the web explicitly. We go out of our way to take advantage of the features of the platform and make sure that it works well within that context. And one of the benefits of that happens to be that it is a lot less complex than some of the native APIs that it's wrapping. This slide does not scroll. So this is, once again, a one triangle draw. This is WebGL, that's WebGPU. It is a little bit more verbose, but not significantly so. It still fits under 100 lines. And that's pretty good as far as graphics APIs go. So let's dive in a little bit more to that one triangle example and see the differences between what a WebGL program looks like and what a WebGPU program looks like that are doing basically the same thing. So first we've got initialization. This one, it looks more complicated, but it's all in the name of flexibility. In WebGL, you say, I want, you take a canvas, excuse me, and you say, I want a WebGL context, and it gives it to you, and you're done. In WebGPU, you have to get an adapter, first and foremost, which then gives you a device, which then you can get a context from the canvas and configure it to use with that device, and then you're done. I'm going to hand wave past all of that right now because we'll talk about it more in detail later. But it is more verbose, but there's good reasons for it.
Brendan, quick question.
Yes.
On the previous slide.
Yes.
One thing I know about having a device with an Intel GPU and an NVIDIA GPU is if I want the WebGL context to use the NVIDIA GPU, I need to go into my Windows setting, change Chrome to use the NVIDIA GPU, and then restart it. Restarting Chrome is almost not an option these days. Based on the adapter and device, can that happen at runtime now?
Yes, that's exactly why it's going to happen. And like I said, I'm hand waving it for now. We'll talk about that explicitly later, but that is effectively the reason why we have this division. So next, buffers. There's not too much interesting to say here. They both look about the same. The biggest difference is that we're actually giving it an explicit size here, and that is going to become important because in WebGPU, just about everything that you do after you create an object is immutable. And that's an important feature of the API, even if it seems like it might be a little bit of an inconvenience. And we'll talk about that in a bit.
I might ask you to jump into immutable because maybe not everybody in the class.
Oh, okay. Yes, I apologize. Sometimes you get so deep into these things, you don't know what's jargon and you don't, and what's not. So when I say immutable, I mean that after this buffer is created, we've given it a size here and a usage here, and this will have those properties forevermore. I cannot change the size of the buffer after I've allocated it. I cannot change the usage of the buffer after I've allocated it. I can change the contents of the buffer. So the contents are mutable. The shape of the container is immutable. Again, going to hand wave past a lot of these things. I just kind of want to give you a visual idea of how a lot of these things relate. Shaders in WebGL work very much the same way as shaders in WebGPU. We do use a different shading language now called WGL. It was something designed by the same team that's building out WebGL itself. And it's just designed with an eye towards working on top of all of the various backends that we have. So the one unfortunate thing about it is that with WebGL, you had a lot of examples of how GLSL code works and whatnot. We don't have the same volume of reference material for WGL just yet. Hopefully it will build up over time. But it's also hasn't been a particularly onerous language to work in my experience. So yeah, not too much different in terms of complexity here. And then here we get to what is probably the biggest difference between the two APIs. In WebGL, when you have those shaders, you want to link them together into a program. That's the thing that makes it executable, so that when you say, I want to draw with this program, it can actually do the thing. In WebGPU, we kind of get rid of that program concept, and we now have what are called pipelines. If you're familiar with Vulkan, some of this is going to feel, or D3D12 or anything like that, some of this is going to feel like I'm just repeating some of those concepts, which is intentional. We're borrowing a lot of the same verbiage. But doing the comparison here, the pipeline is like a program in that it pulls in your different shaders, but it also contains things like the shape of your vertex attributes and the render target formats that you're going to be using and the blending that you're going to be doing with the triangle. And there's a lot of state that goes into this. It's a fairly large object. And so this represents one of the biggest differences between the API is how much you have to consider when you're building these. We'll talk about them more later. And then finally, we get to the actual drawing of the triangle. There's a little bit more setup in WebGPU in terms of explicitly starting rendering. In WebGL, we have kind of default frame buffers where like that's the result, or where the result of all of our drawing goes. It's just this default amorphous thing you draw and it happens to show up in the canvas. We're a bit more explicit about it in WebGPU in that we have to actually get that texture that we're rendering to from the canvas. We're going to begin a render pass explicitly. We're going to tell it as part of that that we're clearing that texture and that we want to store the results afterwards instead of discarding them. And then we do the same basic drawing stuff. The biggest thing to notice here is that we don't have any of this buffer layout set up, and that is important. Why is it important? Let's talk about it. And we'll use sandwiches, because why not? So why is WebGPU more efficient than WebGL? We just looked through a whole bunch of example codes. There's some differences, but honestly, it's not that much. We've shifted a couple of things around. Why does one work better than the other? So let's imagine that WebGL is the sandwich shop. Bear with me, this will only take about 5 minutes. It works. Every day you walk into the sandwich shop, you order the same thing from the waiter. He goes off to the kitchen and prepares your order. But the kitchen situation is kind of complicated, and you don't really realize how complicated it is. The chef speaks a different language than you ordered in. The ingredients are all over the place. Certain sandwiches have been deemed health code violations, so you can't order that. They need to reject it if you do. And the only way that this operates smoothly at all is if the waiter is doing tons of work on the way back to the kitchen every single time to translate your order, reorganize the ingredients list, check for health code violations, so on and so forth. It's a lot of responsibility to put on the one guy. Then one day, the WebGPU deli opens up next door, and they have a weird rule. When you come in, the very first thing you can do before you order anything is register your order with the front desk. They give you a gigantic paper form, you fill it out, you hand it off to them, and then once they've approved it, they come back to you and go, your sandwich is now known as the 53. Okay, so you order the 53, and it comes out to you, and you're like, that's great, that felt like way too much work for one sandwich. But the next day you come in and you go, the 53, and your sandwich is out to you in record time. And that's amazing. But there's a plot twist. Turns out that both of these use the exact same kitchen. Same chef, same crazy ingredient layout, same health code violations. Why was one faster? Well, it's pretty simple. It's because when you submitted your order to the front desk, they took the time to translate it, to reorder it, to validate it once, cache that off somewhere, and then the waiter didn't have to do it every time thereafter. You've basically made a contract with the shop that when you come in, you're going to order something, you're not going to change it in any way, and they will know exactly how to do that. And in fact, they've already prepped the most efficient way to do that because you've told them up front. And this is where the speed up comes from. It might feel annoying to you as a developer if you're familiar with the old way of doing things. It can even be intimidating, but now you're far less reliant on the waiter, who, in case you have not picked up on it, is the graphics driver in this scenario, being clever to speed things up. And that's where a lot of the problems that people had with OpenGL and the older APIs came from. The graphics drivers had to be extraordinarily clever to make things function at all, because so much of the state was coming in real time. If they didn't pull all sorts of crazy assumptions and tricks, things would just go slow. And because they were making a bunch of assumptions and tricks, if you did something that fell outside of their expectations, then your performance was gone. We can avoid all of that with a more explicit upfront API. And you can see how these map. This is all state that was happening at draw time in WebGL. It was happening right before you told it how many triangles to draw. Whereas this is all state that's happening during the setup in WebGPU. It's all the same stuff. You can see here we've got the array stride, we've got the shader locations, we've got the offset into the buffer, we've got the shape of the particular attribute, and we've got the topology of the triangles. But now we're doing it ahead of time. We're making that strong contract with the GPU. This is what I'm going to be doing in the future, and I'm not going to change it. That pipeline has a lot of state in it. This is all stuff that you can set as part of that same object. And in some cases, like the buffers here, you can actually set arrays of that information as part of the same object. It's a lot. There's more of it. It keeps going. We have depth stencil state and primitive state and multi-sample state. This was vertex and fragment shader state. It requires a different way of thinking about how you're feeding information to the GPU. And that can make like porting over something that may have been built in WebGL a little difficult in some cases, but it is worth it because the performance is going to be much better, much more predictable. So I hand waved a lot through that first section. Let's stop hand waving and talk a little bit more about some of the core concepts in the API. So as we mentioned earlier, we start off with this thing called an adapter. You get it from navigator.gpu, and adapters are more or less a representation of the GPUs available to your system. It can be software, but you can detect if it is and avoid it if you really want to, so you can guarantee that you're always getting hardware. And we're not going to give you a whole list of the adapters that are available on the system. That's kind of a privacy thing for the web. But we will allow you to make requests about the properties of the adapter that you want. So in many laptops, you're going to have a discrete GPU and an integrated GPU. The integrated GPU is usually one that's like attached to your CPU. It's usually more efficient, but it's not as powerful. You can explicitly request that if you want and say, hey, I actually want the low powered GPU. This is because whatever page you're building, you want to be battery conscious. You don't want to have all the fans spin up when somebody views it. This is like if you're putting just a little thing in the corner or you're doing an ad or something like that, you should be using these kind of properties. Or you can explicitly say, hey, I want the high power one because I'm doing a game. I want as much triangle pushing power as you are willing to give me. The adapter also gives some information about like the type of GPU that you've got, such as like the vendor and the general architecture. This is so that if you happen to notice that your application has bugs on certain devices, you can do preemptive workarounds. And then it'll list the features and limits available to you, which we'll talk about more in just a moment. From the adapter, you get a device, kind of the logical GPU device, and this is the primary interface for the API. This is very equivalent to the WebGL rendering context in that most of the things that you do with the API are going to go through it, especially all of the creation of buffers and textures and anything else that might be needed. Yes. Oh no. Do I have a power adapter over here? Thank you. Which one?
It's right here. Oh, you can connect yours, I think.
Yeah, okay. We apologize for this break.
If any of you have any questions, feel free to ask.
Yes, please. All right. Yes.
There was a reason at the time of why it was decided for WebGL to make this sort of access instruction mutable in the future, like for example, setting the address pointer and all those instructions. So there was no particular reason.
The reason is it was 1993.
Okay.
Like honestly, it was very much a it was very much something that came from that time period. The software, excuse me, the software development practices back then weren't quite as like object oriented and whatnot as we have now. Um, Having bits of state that you went out and twiddled tended to be the fastest way to interact with a lot of the hardware back then. And GPUs at the time, like they weren't actually even GPUs, they were graphics cards. GPUs tend to be more general in what they can do. And these were fixed state machines. They were very, very narrow in their functionality. They didn't have nearly as much state. And so it was a reasonable, sensible design decision at the time. And I don't think that the developers at that point had any idea how far into the future their API would be carried and how different the hardware that it was driving would look like. So it's not necessarily a bad design, it's just one that was of its time and didn't particularly evolve gracefully. So coming back to this, the GPU device, like I said, it's from, and it has a queue for executing commands. Now, I mentioned that the adapter has features and limits, and the device has them too. These are things that the API or the adapter communicates to you as like the full extent of what it can do. Features are roughly equivalent to WebGL's extensions. They cover things that not every GPU is capable of, and oftentimes this falls into things like compressed textures. Compressed textures are a thing that like every GPU could do it, but there's patent reasons behind why some GPUs only do some formats. And so we can't guarantee access to them across the entire hardware spectrum. Therefore, they become a feature. You have to tell the device when you're creating it, I want to use these features with you. And in doing so, you're effectively opting into incompatibility. You're saying, I know that this may not be available on every system, and I'm making the choice to use it because I know I want to use it on this system. For something like compressed textures, you can actually just look at the list that the adapter tells you and pick the format that you want to use and maybe recompress them on the fly or something like that. I have a couple of demos that do that. For the limits, these are numeric limits that tell you the extent of a GPU's capability. Things like how big of a texture can I have? Excuse me. Or how many vertex buffers can I have bound at a single time? Now, for WebGPU, there is encoded into the spec a baseline that every WebGPU implementation must implement. So you can go and look at that and say, I know that if I get back a WebGPU device at all, I have at least these capabilities. And that's true across the entire ecosystem. And they're not too bad. Like the limits that we can give you as a baseline are pretty reasonable. You can do an awful lot with them, but in cases where you want and need to do more, you can look at what the adapter advertises and tell the GPU or the device, again, on creation, I actually need textures that are able to be up to this big, higher than the default. And again, you're opting into incompatibility. You either need to dynamically choose a different value on lower capability devices, or you're just making the conscious choice to say, I don't work on devices that don't have that capability. And then the last kind of initialization section of objects that we get back is the canvas context. Now this comes from the canvas like the WebGL context does, but it is way, way more limited. About the only thing you can do with it is configure it to work with the device and get a texture out of it. That's it. And this is actually a good thing, because what it means is that I can create a device that has no canvas attached to it whatsoever and go do, say, a bunch of compute work and never worry about having some little hidden canvas in the corner of the screen or anything like that. Alternatively, I could have 4 or 5 different canvases that all then connect to the same device. And the device can render to each of their textures individually. And you can do things much more easily, like, say, 4-pane graphics editors, like Maya style or something like that. That was actually pretty hard to do with WebGL. And this was one of the areas where we took developer feedback and said, yeah, let's break that pattern and do something more convenient, even if it adds a little bit of complexity to the API. Now, since y'all have been learning about graphics APIs, I'm going to assume that you're generally familiar with the concepts of buffers and textures. I'm not going to spend too much time on it. The thing that I will point out as a difference from WebGL is we now have texture views. This is something that is present in all the modern APIs, and it's basically just a pointer to a range of texture subresources. This is the thing that you'll be interacting with anytime you're dealing with shaders or something like that, because generally we want to know, like, do you want to use the full texture? Do you only want to look at a single layer of it? Do you want to look at a texture with 6 layers, but you want to treat it as a cube map? That happens at the texture view level. So again, a little bit more complexity, but a lot more flexibility. As I mentioned earlier, we have a new shading language. And I'm going to just give this as an example side by side that you can use to compare, or no, sorry, these are both WGL. And just to give you a sense of like what it looks like and feels like, the API is kind of, or the language is kind of designed after Rust. And so if you're familiar with that, you might be familiar with some of the syntax that shows up here. I can't tell if that's a good comparison to Rust or a bad. There's some laughter going on here. But I could spend an entire presentation just talking about the shader language itself, and I'm not going to. What I will point out is that it's got basically all of the features that you would expect if you're familiar with any other shading language, GLSL, HLSL, anything like that. You can do all your vector math, matrix math, and everything else. And I've personally found it to be fairly nice to work in. Moving on, we have pipelines. We talked a little bit about the render pipelines previously. There's also a compute pipeline flavor. And these link together the shader modules. And for the render pipeline, gives a whole slew of state that, once again, is immutable after you create it, which is a pattern that you see all throughout the API. And then the device itself has a queue. Now, the queue is anytime you actually want something to happen on the GPU, you send it through the queue. It executes command buffers and also has a couple of helper functions on it, write buffer and write texture. These are just convenient ways to say, I have a buffer, I want you to stuff this data into it now. There are other ways to do that through mapping and copying, but this is way more convenient and in most cases actually faster. And then we get down to where you would end up spending the majority of a draw loop, which is creating command buffers. Now, for command buffers, we have this concept of a command encoder. You're going to get that out, and it gives you the ability to record a whole bunch of commands, finish it at the end, gives you back a handle that represents everything you just recorded, and then you hand that off to the queue and say, submit it. This is just a distinct concept from the queue, because it might feel like, well, why don't I just tell the queue to do all this directly? But it's a distinct concept from the queue, specifically because we do intend to add multi-threading to the API at some point. It is not there in version 1. It will not be in the initial thing that gets shipped. But eventually, the idea is that you will be able to do this in one worker, one thread, toss it over the thread boundary, and have it submit on another. And that's a very common pattern in the native world for getting much better performance out of your applications. So you can see here some examples of like the type of things that happen in command encoder. You can do a lot of different copies between buffers, and textures. And then you can also begin either a compute pass or a render pass. And within those respective passes are where you would do all the work with a shader of the compute or render variety. The passes themselves, we've seen examples of this kind of scattered throughout a bunch of the previous slides. Render passes are the more complex ones. You have to start them out by telling them all sorts of information about what the color and depth attachments are, and am I multi-sampled or not, and what do I do to resolve if I'm multi-sampled. This is a very simple example. And then you can get into there and say, okay, I'm going to set up my pipelines and my bind groups and my vertex buffers and draw. On the compute path side, you're setting pipelines and bind groups and dispatching work groups, because draw is not an appropriate verb for compute. Now, bind groups is something that we haven't talked about yet, and we're going to, because this is probably, in my estimation, the most confusing part of the API. So I wanted to make sure that we spent a little bit of time on it. If there's any questions so far, now's a good point to pause and ask them, so feel free. Yes. WGL. Thank you. We call it WGL. And there are publicly stated motivations and privately stated motivations for this. The publicly stated motivations are that we wanted something that was in control of the working group, that we could evolve along with the rest of the language, that we could make specific choices about how it would wrap the various backends to make sure that we achieve the best compatibility going forward, stuff like that. The private reasons are legal, and I'm not going to get into them. But yeah, there was a lot of forces pushing towards developing our own shading language. And I will be perfectly honest and say I was not a particularly big fan of that choice when it was made, but I've since come around after working with the API for a while. I do find it to be a nice language to work in. Yes.
What would you say is like the hard boundary between what is like achievable through WebGPU versus something Vulkan?
That's a really good question. So in general, there's always going to be a little bit of a performance delta. It's probably not as big as you might think, but we're just going through more layers and we're interacting primarily with JavaScript. You can actually use the WebGPU API in native code. The Chrome team has an implementation of it that we call Dawn, and it's got a C and a C++ API. You could use it if you want to. Might be more convenient for some projects, but in general, we're just going through more layers, more validation, whatnot, and so you're not going to be able to achieve exactly a peak performance that you might get from something like Vulkan. Also, because we are doing those abstractions, we're not always going to make the exact best choice for any given platform in favor of doing something that's more generic. And then the final thing is that there are extensions and features that Vulkan or the other APIs might have that for whatever reason we haven't been able to bring over to WebGPU yet. An example of this would be ray tracing. Ray tracing, very popular right now. All of the newer GPUs can do it. We have ways of doing it on all of the new APIs. We don't have a way of doing it in WebGPU yet. Typically what's going to happen for stuff like that is we're going to want to, excuse me, wait and see how the native APIs kind of shake out their different variants of the API, or the feature, excuse me. Find kind of the common ground, what we can expose reliably and have it work across all platforms, and then expose it as one of those opt-in features for WebGPU that I was talking about earlier. This is something we've already seen play out in WebGL, where we had a whole bunch of extensions that just kind of grew over time. And I expect the same thing to happen for WebGPU. And yeah, there's always going to be some latency. We kind of can't be on the cutting edge of things. So like some of the newest features are things like mesh shaders, which are really, really cool. And I wish we could play with them on the web, but it's just going to take a little while for us to see how that feature settles down into the hardware before we can reliably expose it to everybody else. But it will come.
To branch off of that, especially since you're from Google, Stadia, rest in peace.
I have so many thoughts and I'm not going to share them. But
like Stadia is streaming, so like the underlying games that it is streaming is run more using like something like Vulkan, right? But it is just streamed through the web. But did WebGL like play a major role in like how that product worked, and like could WebGPU have like contributed to that?
That is an excellent question. I don't know off the top of my head if any of the client side for Stadia, which was fairly thin, use something like WebGL or not. I know it did make use of a lot of web APIs, some of which I was involved in. It used like the Gamepad API that I helped develop. But it's not clear to me that they would have used something like WebGL. I think they would have more likely streamed it to like a video element, because that's all it really was on the client side. On the server side, it was Vulkan. So yeah, if you're asking would WebGPU have saved Stadia, the answer is definitely no. But yeah, they did make interesting use of a lot of web APIs in terms of how they presented it to the user. Okay, well, we'll move along. So let's talk about how we expose some of those buffers and textures and everything to shaders in WebGPU. Because like I said, this is probably one of the more confusing parts of it. At least it was one of the things that took me the longest to get used to. So in WebGL, if you want to get a uniform, a piece of data into a shader, it is kind of embarrassingly easy. You say, hey, shader, what's the position or what's the handle for a value with this name? And it gives you back a handle and you say, okay, great, set that handle to this value. And you're done. And that's great. It's easy. Really slow, but it is easy. As a developer, it's nice. WebGPU is a little bit more complicated. So first off, when you declare your shader, you're going to give everything these explicit numeric groups and bindings. So you can see here, we've got group 0, binding 0, that is associated with these uniforms, group 1, binding 1, group 1, binding 2, so on and so forth. So yes, we need to declare the binding in the shader itself. We give everything groups, we give everything bindings. What just happened there? There we go. And then in JavaScript, we're going to go and repeat all that information. And this feels like a pain, but basically you're going to go in and say, I'm going to create a bind group layout. And in this, you're going to match up the binding numbers with the binding numbers that you gave in the shader. You're going to match up the types of your assets or your resources with the types that you declared in the shader. And it's going to give you out a handle for that thing, the bind group layout. When you create pipelines, you give them a whole group of layouts that are compiled through something called a pipeline layout. Each element in the pipeline layout needs to associate with one of those groups that are in your shader. You give it there, and if you don't match up all of those things perfectly, this will fail. So good luck with that. Now there is an easier way to do this, where you can just, instead of giving a pipeline layout here, you can just say auto. And it will do all of that for you. And that sounds like a good deal. And for some cases, it is. If you're going to build like a compute shader that you only use in one particular scenario, and you're not sharing the bind groups with anything else, then yes, just put auto in there and life will be easier and you can move on. But it's pretty important for efficiency that we don't encourage you to do that all the time.
So Brandon, on the slide before
Yes.
before that one with the arrows, Isn't this just a recipe for people to make mistakes and errors in their code?
It totally is. Yes, but there is a good reason for it, and I'll get to that in a second. It is a royal pain to type all this out. It really, truly is. But it enables a very important pattern that we'll get to in about like 2 slides. So after you create the bind group layout, and you can create some pipelines with the bind group layout, you can also create the bind groups themselves. Now, the bind groups are basically just a set of pointers off to various resources that you've already created. And again, they're going to match up with the things that you've already set in the shader or the bind group layout itself. You can see here that we're passing in the layout that we've already created. And there we go. Yes, we have to match up the bindings again. We're matching, oh, go back. And we're going to match up the resource types with the things that are already declared in here. At this point, you can also do things like give it offsets or sizes, so you can specify ranges of buffers. You pass in texture views instead of textures, so you can give subgroup layouts and stuff like that. So you've got some flexibility here, but fundamentally, you're just repeating the same thing again and giving it actual resources this time. So why do we do all that? Well, in the really simple case, this is how you're going to end up using that at draw time. First off, it's important to note that the resources that you gave to the bind group, it's not a snapshot, it's just a pointer. And so if I come in here and write new content into that buffer at the beginning of every frame, then this will pick it up and I'll see it, that new content in the shader every frame. This is how you set a uniform in WebGPU. A little bit more complicated. But then, yeah, in the whatever pass we're going to do, compute or render, we're going to set the pipeline. We're going to call set bind group once for each group. This is the group number, saying I'm setting this group to these and this group to that. And then I'm going to dispatch some work or draw some triangles. And it will use the resources from these bind groups in the shader. And that's how you get matrices and lights and transforms and textures and everything else. So the reason why we make you go through all that pain is because it's very important that we be able to actually share the layouts of these things across multiple shaders. So what you will typically actually do is not declare the shader first. You're going to decide the layout first. And then you're going to have multiple shaders that all have the same layout. So you'll have like a struct. A really easy way to think about this is if you're doing rendering, then there's going to be a certain set of variables that come along with every single thing that you want to render. The camera is a good example. You're going to have certain variables that describe what the camera is doing in your world, the virtual camera. This is going to be a view matrix, a projection matrix, maybe an inverse of one of those matrices, position, who knows, whatever you need for your scene. And the important thing about it is that's probably not going to change for the entirety of your render loop. If it did, your render would come out really weird. So in the WebGL model of things, what would happen is you would set a program, and then you would reset all of those camera variables. Then you'd set another program and reset all the camera variables. I'll get to you in just a second. What we really want to enable here, and you can kind of do in WebGL too, but we're trying to take the concept further, is say, okay, if you've got a set of stuff that's not going to change for the entirety of your render loop, set it once. And then every single pipeline after that, if it used the same layout, the same bind group layout for those variables, it'll just pick that up and say, great, you don't need to change anything. It's already cached in the GPU memory. It's much more efficient that way. And so as long as you construct your pipelines to be, or your shaders to be cognizant of that, you get more efficient. You can also start to kind of cascade that down through the other layers of things. So if you think about a generic scene of a real-time 3D game or something, you might have a whole bunch of materials that are shared across different meshes. There's a carpet material or a brick material or something like that. And this is going to be used across 50 different meshes. Well, we don't want to reset that material every single time we draw one of those meshes. So instead, you can say, oh, I'm going to loop through all of my materials, set the pipeline that is associated with that material, and then set the bind group that's associated with that. I only have to do that once. Now I can loop through all my meshes that use that material, set up the state for them, the vertex buffers and whatnot, and then set bind groups that contain just what that particular mesh needs. You kind of want to do this in order of how frequently they change. And then I can draw a whole bunch of those. I probably want to use instancing, but I'm not here. And like the amount of times that I have to set bind groups becomes much, much less because I'm communicating it only when things actually need to change. So you had a question?
Oh yeah. Can I make this like very weird analogy that WebGPU is more object oriented compared to like WebGL, since like WebGL feels more imperative compared to object.
Absolutely, that is a perfectly apt analogy. WebGL is very much more imperative. It's very much about going in and flipping bits of global state back and forth, and then resetting state anytime you need to. Whereas WebGPU is much more object-oriented. It is much less concerned about global state and keeping state localized to whatever you're doing at the moment, and making sure that you can reuse as many of those objects as possible. In the end, it's not that much like this is more complex than the WebGL equivalents, but it's all in the name of performance and allowing you to construct your rendering in such a way that you're minimizing the amount of state that you're doing. But in terms of like what's being sent through to the GPU at the end of the day, it's actually not all that different. It's just trying to express it in a way that the GPU understands more efficiently. So that's kind of the overview of a lot of the core APIs, how you interact with it. It is complex, just like any GPU API, even WebGL, for as much as I say, oh, it's easier in there, WebGL is still complex to use. There are still lots of opportunities for errors. And so any good GPU API needs to be able to help you figure out when things go wrong, because they will go wrong. So let's look at how this happens in WebGL. We can take a little chunk of a program like this, and I can tell you there's an error in it. Don't bother to find it, it doesn't really matter. And we can say, hey, WebGL, I ran this and I didn't get the triangle that I expected. Why? And WebGL will tell you, thank you. That was helpful. I appreciate that. I took offense to this, and I made it my personal mission on the Chrome team to ensure that when something went wrong with WebGPU, we would give you more information than you would know what to do with about what the error just was. So let's look at how that same issue plays out in WebGPU. Roughly equivalent code, roughly equivalent bug. If you try to run this in WebGPU, you won't get a triangle, but you will get something like this in Chrome's error console. It says, hey, you have a buffer usage, this, that doesn't include vertex. And we noticed that while you were calling set vertex buffer. You can kind of make the inference, hey, if I'm setting something as a vertex buffer, I should be able to use it as a vertex. Now we can look at this and say, oh, hey, look, this is the usage that it's telling me I have, which corresponds to this. And that's the function that it told me I was calling when it noticed the problem. And so I can make the inference that this needed to include vertex as one of its usages before I called that. Cool, I can fix that. Now, that was a simple enough issue, but obviously most cases are not that simple. So what do we do when we need more context about what went wrong? Well, let me introduce labels. They are your favorite debugging tool. Every single object in WebGPU has the ability to be given a label. The label is whatever the crap you want. I don't care. It is just a string. And it's something that's meaningful to you. So in this case, we can say, hey, I'm going to give my vertex buffer a label that says these are player vertices. And my pass encoder for the render pass, I'm going to say that this is my primary render pass. And then when I get that exact same error from previously, those labels will now show up in the error message, which tells me a lot more about where it came from. Hey, this error came about when I was trying to set the player vertices. I have a much better idea of where that came from now. But we can do better. So we're going to give you your second favorite debugging tool, which is debug groups. Now, debug groups are just things that you can push and pop onto the stack. They're just strings. But you can use them to give yourself meaningful labels for which section of the code that you're in. And it is a stack. So we can say, hey, I'm going to do a command encoder here, and I'm going to label it, this is my main render loop. In this portion of it, I'm going to be rendering a scene. Within here, I'm probably going to be doing things like render player, render wall, render whatever. And then I'm going to have another section that's rendering UI and so on and so forth. Then when a failure comes out, we will return all of these back to you as a debug stack, so you can get additional context for figuring out where this came from. It is my personal mission to make sure that when you get an error, as long as you're setting these things, you can go exactly to where it was and you will know exactly what the problem is.
Thank you for adding printfs into a
Yes, this is printfs on steroids. Here's another example, a little bit more detailed from one of my apps that was failing. You can see here the error was, hey, you tried to give me a binding offset of 256 and the buffer size is only 144. Obviously that doesn't work. This was entry 0 in a bind group layout, and it came from this call during this stack, so on and so forth. Makes things a lot better. Now, an important note here is, one, setting these labels is basically free. Don't try to strip them out for release mode or anything like that. There's really no overhead to it. They only really have an impact when something went wrong, in which case you don't care about performance anymore anyways, you just want to know why it went wrong. So just use them everywhere. The other thing to note is that if you are using native debugging tools, such as RenderDoc or Pix or anything like that, these labels also get passed all the way down to that. So if you can pull up a RenderDoc trace of what you're doing in WebGPU, you get all your nice flame graphs and everything, they will be labeled appropriately with the thing that you told it in the browser. So again, we're just going way out of our way to make sure that debugging these things is as painless as GPU debugging can be. Yes.
Yes, I have a question about like speaking from the perspective of like a developer of graphics API, like what is like the developer side like headache for including those error messages? Because in my in my previous like I worked for a startup company which also works on graphics APIs and GPU parallel programming. And obviously, people a lot of like using the language are complaining about like not including like enough error messages or like have something like similar to like GL and valid operation and not giving like very nice information of the entire like debug trace and stack calls. So I was just wondering, what is the developer side like headache?
Yeah.
Including
so for me specifically, the headaches came from a couple of places. One is simply like, it's a lot of strings to type. And I wanted to make sure that they all sounded the same. So like we have a style guide for like how the errors should be written to make sure that we're stating things in the right tense and using the same verbiage and silly things like that. And that was harder than you would think to put together. But the other side of it was, that's a lot of information and we want to make sure that we aren't impacting performance at all. And so we had to set up some patterns in the code to ensure that you could associate these error messages with a piece of code and that they would surface at the right time when that code was hit, but that no computation would be done for them unless you actually were in the error state. We don't want to build a partial error string and then say, oh, everything succeeded, toss it out. Like that would be a performance hit. It probably wouldn't even be a terrible performance hit, but it's a graphics API. We don't want to introduce overheads. So that was a little bit of a pain to figure out the right patterns for making sure that we weren't actually hurting performance by being so verbose. And I don't really know how to describe those patterns verbally. So if you're really interested, I could point you at the spots in the code where we actually generate some of them so you can see. But I'll have to do that after.
I may be slightly ignorant about the other native graphics APIs in Vulkan Metal. Do they have similar things, or do you think they can get inspired by similar methods?
They have similar facilities. I will say that they are not at all easy to get to. Like the Vulkan version of this is, you will get back a handle, and then there's like a generic set property function, I think. And you have a whole huge list of enums of different properties that you can set on the object. And then one of them is label, but it's not called label, it's called something far more obscure. And then you just pass in a void star, which in this case happens to be a UTF-8 encoded string. It's not very apparent that it's there, but it is there. And that's why we were able to actually pass this data all the way down through to the native tooling. Hopefully we've made it far more accessible than the native APIs do. Metal is actually pretty good about this. They just have like a property on their objects and you set it and it's good. So we're getting close to wrapping up here. Hopefully I haven't been too boring. You've been a great audience. But I wanted to go over a couple of really high level tips for if you should be using WebGPU in the future, ways to keep it performant. The first and probably most important thing is you want to try to minimize the number of pipelines that you use. Now, this is something that comes up in the native side too, but it's really easy to fall into the trap of not doing this because, like in general, the more pipelines you have, the more state switching you're going to be doing and the less performant you're going to be. State switching is always the thing that you want to avoid. Now, depending on the application that you're doing, this might be trivial. You can just say, okay, I've like everything renders with the same pipeline, and so I've got like 3 of them, and it's good. But there's certain cases where, say, if you're loading a GLTF file, if you're not familiar, GLTF is a fairly popular model format, and it's structured in such a way that the geometry in there does not follow any guaranteed patterns. And because the layout of your geometry is something that you have to feed into the pipeline creation, this makes it so that you don't have any guarantees. And the easiest pattern to fall back on is just, well, maybe I'll just create a pipeline per piece of geometry. And that's not the right thing when you're trying to be efficient about it. I wrote a whole article about just that topic. And I'll let you go hunt down the slides and read that later if you want. But it can be a little bit of work, but minimizing the number of pipelines that you're using is absolutely worth it, even if you have to do some manual deduping and whatnot. As an antidote to support this, on the Vulkan side, there's a game Doom Eternal. It's a Vulkan game, fairly well performing. That team has said that the entirety of that game runs on 50 pipelines. Now, that's for a project that size, that's probably fairly aspirational. Like that's I'm sure a feat of engineering, but kind of shows that like at that level of development, proud of how many pipelines they were able to reduce it down to. It tells you how much it means to reduce the number of pipelines that you're using. The next thing that I'll say about pipelines is you want to create them in advance. This is something that I've seen bite multiple teams already in just their exploratory WebGPU work. So what happens here is if I create a pipeline and then I immediately turn around and use the pipeline as part of a submit, this will actually work. It will do the right thing. It will give you the correct results on screen. It will just not do it fast. Because what happens when I kick off this work is that we will give you back a handle immediately, but then the actual work goes off to the GPU to finish completing. And pipeline creation is one of the most expensive things you can do. It can take tens of milliseconds depending on the device that you're on, hundreds of milliseconds depending on how complex your shader is. And so we kick off this thread, it's working in the background, and if I just hold on to that handle, do some more loading work, whatever, come back to it and use it, maybe 3 seconds later, you're fine, because it's had plenty of time to compile. But if I try to use it right away, we'll hit this point in the GPU execution, and it'll say, that resource is not ready, stop the world. Wait for that thread to join, and now I can continue on my way. What this looks like in practice is we've seen an example project from somebody, fairly large company, where there was a woman who was running around with a stick, and it was a magic stick, and every time she swung it, there was particles that came off the end. But the trick was that the particles, the pipeline that generated the particles did not compile. They didn't call create render pipeline until the moment it was first needed. And so what would happen is she'd go, and then the particles would go, and it just wouldn't work out at all. And there was some frustration at this, and it was because they were compiling the pipeline immediately before using it. You want to give your pipelines time to breathe. But more efficiently, we also have these versions of the same functions called async. Create compute pipeline async, create render pipeline async. These are structured differently in that they don't give you back the handle right away, they give you a promise instead. And then the promise resolves only when the pipeline is able to be used without any stalls. If you can, you want to use this pattern as much as possible because it will guarantee you that you're never going to have a hitch in your rendering because you're waiting on a pipeline. Now, not every application is going to be able to use this pattern. In some cases, you want to try and start a pipeline compiling and then do a few more things. And then you'll get to a point where you're like, well, I need it now, whether it's ready or not. And sometimes you just have to take the hit for the jank that that's going to cause. But depending on your application, that might be the right choice. We don't know. So we give you both variants of this function.
Do all WebGPU APIs have async counterparts?
Only the pipelines really need them. Everything else is lightweight enough that it's generally not a problem. Like you would have to be creating some really massive buffers for that to be the thing that causes jank. But pipelines can take a good long while, especially depending on the backend that you're going through. Like the DirectX compiler is not fast. And then finally, the last thing I'll mention in terms of tips is we've introduced a feature into WebGPU called render bundles. And this is specifically to get around some of the issues that we've had with WebGPU in the past where JavaScript was the bottleneck. JavaScript is not necessarily known as being a fast API. And it's better than you might think, but there's still plenty of times where you can start starving your GPU by not being able to feed it commands fast enough with JavaScript. So what a render bundle is basically a partial repeatable render pass, where I come in and say, okay, I'm going to record a whole bunch of draw commands and set pipelines and everything else that I can do in a render pass, except for like setting viewports. That's about the only thing you can't do. And then it gives me back this object that during a normal render pass, I can then just say, hey, replay that. And it will take all the commands that you recorded previously and like way down the stack on the GPU level, replay them back into the GPU as quickly as it can. This is great for avoiding JavaScript work as long as you are doing repeatable work, because the render bundle can't be modified like everything else, it's mutable. And so, for example, if you're doing some sort of first-person game or anything where you've got a camera swinging around like this, and you were doing any sort of frustum culling, render bundle is probably not the right thing to use in that situation, because you could record the drawing of the entire room, but you don't really want to be drawing the stuff behind you, and if the camera is moving around quite a bit, that's just going to be wasting draw commands. But if you have something that's consistently on screen, frame after frame, and the only thing that's changing about how you draw it is the uniforms and buffers and textures that go into it, render bundles are great. The metaballs thing that I was showing earlier, that whole thing is drawn in like one render bundle. And it makes the JavaScript time for that particular scene like less than a millisecond. It's ridiculous. Yes.
So how does this stuff interface with like React, or does it?
So we don't have any explicit interface with React. I will admit that I don't have a lot of experience using React directly, but my expectation is that you can just call it from React directly. And the biggest thing that you're going to need to manage there is like the canvas elements. React is going to want to have control of where those are positioned and whatnot, and then everything else can just kind of happen distinct from that API.
Brandon, I'll turn that question over to Sean and Gabby, who work easier. I mean, you guys probably have a better answer to that.
I think they're tangential enough that it doesn't really matter. They're two separate things. One's dealing more with DOM and the other React.
Yes.
How would you go about like measuring and monitoring where the bottlenecks are exactly? Like for example, you said JavaScript, but how do I know JavaScript is the main cause of bottlenecks?
That's a good question. So I wish I had a slide for this. That would have been great. What I tend to use is Chrome has, and all the browsers, but as a Chrome engineer, I'm going to talk about Chrome, obviously. Chrome has development tools within it that allow you to capture profiles of various aspects of the page. There's actually two different profilers in it. There's the one that's in the DevTools panel that you can get to on any page, and then there's, if you go to about:tracing, there's a much more detailed one, and these can both capture various aspects of what's going on your page. It's not always like super easy to tease out like, oh yes, this is obviously JavaScript that's bogging me down versus the GPU. If you look at some of the traces, you can see like a whole ton of JavaScript on your flame graph and then a little bit of GPU, and you're like, okay, well that's JavaScript. But then there's also plenty of things like, if it's not JavaScript, well then what is it? Is it my fragment? Am I bottlenecked on fragment processing, on vertex processing, on like, am I just waiting on different assets to be, or resources to be finished so they can be used in the next render pass or something like that? Those are a little bit harder, and you have to start using some techniques that just apply to all of the graphics APIs, native or not. So for example, if you want to know if something is fragment bound, in that the fragment shaders are the thing that's taking up the most time, the most effective thing that I usually find is, well, just take the canvas and turn it down to half size or quarter size. And if suddenly you start going faster, well, you're probably spending too much time processing fragments because there's less of them now and things are going faster. But if you do that and you get no change in performance, then your bottleneck's coming from somewhere else. Yes.
I've seen some like WebGPU samples and applications using TypeScript. What would be like recommended for people who want to do WebGPU applications to write their code in TypeScript?
Yeah, sure. In fact, we have a we have a conformance test suite for WebGPU that is entirely written in TypeScript. And if you go online and you search for WebGPU samples, you'll find some that are hosted by Austin Eng from, again, this program, and they're all written in TypeScript as well. It works very well within the bounds of the TypeScript framework. I've done some of the maintenance for the TypeScript types for WebGPU myself. We've been keeping it up to date as we make changes to the spec, so it should be something that works really well. There's some additional resources here. I'm not going to get into most of them because if you want to dive into any of them, I expect that you'll just go through the slides. But the last thing that I wanted to bring up is I heard that this is a group that might appreciate some career advice. I don't know that I'm the best to give it. I haven't been actively looking for a job in graphics for a good long time, and I kind of accidentally fell into one that I was in. But it is worth noting that the reason I am in the position that I'm in right now is because I was doing interesting stuff, or at least stuff that I thought was interesting, and putting it online. The reason I got into the tech industry in the Bay Area is because I developed a matrix library. It's called GL Matrix, and I put it online because nobody else had done a matrix library for JavaScript that I felt was fast enough. I didn't expect anybody else to use it, but I threw it up on GitHub anyways, and that got me a job.
If I can pause you there.
Yeah.
Project 5 WebGL. So we have either a WebGL or a Vulkan project for Project 5, depending on what they want to choose. Project 5 uses GL Matrix, and the author of GL Matrix is standing in front of you.
So yeah, like putting the work that I had done online was something that was instrumental for allowing other people to see the type of work that I do. And in the same thread, if you're looking for a job in computer graphics specifically, I would really encourage you to take advantage of WebGL, WebGPU, something on the web to show off what you know about graphics in some way, shape, or form. And this applies even if you don't want to touch the web at all professionally. That's fine. That's totally cool. But the concepts that are going to be present in any of those APIs can be expressed on the web. Unless the thing that you're trying very specifically to show off is, I know the ray tracing APIs or something like that. But like if it's, I know these shadowing techniques, I know PBR shaders, I know all this, you can express that on the web. And that is such a powerful thing. Like I was talking about at the very beginning of all this, to have something embedded in your resume. You send somebody an online resume and there is a proof of your knowledge of graphics spinning on the page right there. That's cool. That's eye-catching. That's powerful. And it's worth dipping your toes into the web if for no other reason than to catch somebody, a prospective employer's eye. This is not a black slide. What happened there? Hold on. Cool, we're just gonna leave that there. So other things, because you all are working in graphics rendering, I think this applies. Building your own engine, your own rendering engine, is a fun thing to do. I've done it a lot. It's not necessarily a career advancing thing to do. So if you're in a position where you're looking to build a project of any sort, unless the project is, I want to build an engine and like, you know, maintain it and try to, like, if that's your marketable thing, then whatever. But if you're just trying to get something done, fall back to existing toolkits or engines or whatnot, because there's so much of this that is complex and it just takes so much time and energy to go through beyond just knowing how the APIs work. Things like loading assets and combining with sound and physics and controls and everything like that. You really want to rely on the work that other people have done to help get you bootstrapped fast. Now,
I don't know if I can just chime in there. As somebody who hires developers, I'm sure Brandon, you can chime in as well. Knowing 3JS, knowing Unity, knowing Unreal is probably more valuable to me than if you've written your own game engine. Like writing your game engine shows that you have experience, you have knowledge, but if you use game engines that I'm using at work, and I'm specifically hiring somebody who knows Unity, I'm going to hire somebody who knows Unity. I'm not going to hire somebody who's written a game engine. So that's an important choice to make.
yeah. Now, there's still room in there to flex your like API muscles. Like if you know Vulkan, if you know WebGPU or WebGL, and you're using these projects that are built on top of them, there's still a lot of room to go in and say, okay, I'm going to use the engine for the majority of what I want, but I have this very specific effect that I want in mind, or this very specific tool that I want to add, or something like that. And that can be really valuable to know how to bend those existing libraries to your will and to add something to it and to make it shine in a way that nobody else is doing. That is really, really valuable. And it often involves getting down in the guts and knowing all of these backend APIs so that you can build on top of it. Also, just like building libraries or tools that complement these existing ecosystems or fill in the gaps in these ecosystems is something that I've seen multiple people build their entire careers on. Like somebody says, well, hey, turns out Unity isn't good at splines. I'm going to build a spline library and make it available on their asset store. I know somebody who's built an entire career around that. So it's an interesting space to play in. And then this is just from personal experience. I'm a software developer. I have no aspirations to be an artist, but I have found it to be one of the most useful things that I've ever done to learn a little bit of Blender. Just like not enough to actually build my own art assets or anything like that. My art assets are still cubes with googly eyes stuck on them. But knowing how to get in there, import assets, tweak them, pull off faces, merge things, reduce the complexity, stuff like that. Like the breakout game that I showed you earlier. I built the whole thing from scratch. None of those art assets were mine. I went on Sketchfab and other sites like that, bought a few assets, used a few Creative Commons assets, took them all into Blender and built the whole level out just by repositioning things, exporting it out, culled all the back faces off of stuff. It's a valuable skill set to know, even if you plan on doing zero art whatsoever. Having some basic functional knowledge of these tools lets you dive in there and get things up and running faster than if you constantly have to go back to an artist and say, hey, can you tweak this thing? Hey, can you export it this way? Hey, can you turn on this flag? I was going to skip this, but you know what? Fine. I'm going to show this slide anyways because it's fun. No. What? Oh, it's not going to let me do it. Okay. Anyways, point being, I wasn't going to go over this slide, but it's also good to know how to identify issues in like art assets. So for example, this is like a screw that came out of somebody who's trying to do a real-time art asset of like a light fixture on a wall. And then they were wondering, why is my map so slow? It has like a million vertices in it. Of course your map is slow. It was this big in world. Like, don't do that. And that is the end of the deck. It has been my honor and privilege to speak to you today. I hope you found it educational. I'm very happy to answer any further questions that you have. Thank you for your time.
And remember, they can be about anything.
I haven't had too hard of a time hearing people, so.
Oh yeah, I can.
And just share your name as well.
Hi, my name is Ayad. Thank you for coming. This was a great lecture. So you mentioned earlier, like one of the restrictions, things you had to keep in mind when developing a web API is like security.
Mhm.
So I was wondering, what other sort of restrictions / limitations you have to keep in mind as a web API developer that would compared to like native API developers?
So, I mean, security and privacy are the big overarching things that we consider all the time. Security in that, like, the web page simply cannot leak information to you that is not owned by the page itself. Now, and on the privacy side, it's like we want to ensure that when you go to a page, it is respecting your privacy by default. Now, there are ways to opt in, but we want to make sure that that always happens with user consent. So, for example, you go to a page and the page wants to use your microphone. That doesn't happen by default. You have to click a button that says, yes, I explicitly allow that, because otherwise it would be a huge privacy violation. We don't end up with too many of those type of issues in an API like this, But what we do end up with is what we collectively term fingerprinting issues. And this is an issue, this is something that we're constantly battling on the web, where if I go to a web page and they want to track you as an individual, a consumer, they're going to look for all sorts of information about your device specifically. And basically, like, there's some software that will take any little shred of information that can be given and collect it into some huge hash and try to figure out who you are. And then when you go to another site, even though those two sites have no knowledge of each other and you haven't explicitly given them any, they can regenerate that same hash and say, ah, this is customer 3761. So we want to try and reduce the amount of uniquely identifying information that is about you. Now, that uniquely identifying information is very rarely like, oh, this is the serial number for my box, but it is things like, I have a device with a screen resolution of X and Y. And I have audio hardware that processes samples at this frequency. And I have a GPU that has this many texture slots in it. And a whole bunch of like really abstract things that you would never really think of as identifying, but when you collect them together, they can be something that very uniquely identifies you, or at least puts you in a very small circle of people. So that is something we have to think about a lot with an API like this, because there's a constant sense of tension. If we want the API to be useful, we have to tell you how many textures you can use. We have to tell you how big they are. We have to be able to communicate this information to you. But if we want it to be private, we want to tell you almost none of that. And so the balance that we try to strike here is we go in and we say, okay, we will let you know that the user is using an NVIDIA GPU. And it's of this class, but we're not going to tell you the model number. I can tell you that it's the 40 series, but I can't tell you it's a 4090 or 4080 or something like that. We can say, yes, they can use all of these baseline limits. This is how big their textures can be and whatnot. But we're not going to tell you the exact number that the hardware advertises when you ask the adapter. Instead, we're going to bucket it into discrete quantized steps. And that way we make sure that if somebody does try to identify you by that, the bucket of people that you fit into is larger and larger and larger. It's a delicate dance, and we don't always get it right, but it's something that's constantly at the back of our mind.
I see.
Have an experience searching on Amazon for, I need a charger, seeing a charger ad on Instagram,
Yeah. Usually that's done through much stupider, more basic means, but yeah, it's the same fundamental concept.
Then another question I had is sort of what's the vision like ultimately for WebGPU? Is it like just supposed to overtake WebGL? I'm asking this specifically because you were talking about the Flash era in the beginning, so wishful thinking,
Yeah, so in terms of like where we want the API to go, my expectation personally, and I think other people who have been working on the API, is that I expect that most real-time graphics that you see on the web will eventually transition over to WebGPU, simply because it's more capable, and in many ways, despite the complexity that we've been talking about, it is easier. I find it easier to work with despite all the bind group madness, because you don't have to think about things like global state. In WebGL, you've got this insane issue where you go in and you say, I want to render a triangle, and it says, I did, and you say, I can't see it. You're like, oh, well, that's because something 5,000 lines up in the source code file said, I want alpha blending to be turned on now. But that's not me, that's not my code, that's from a completely different library, and I had no way of knowing that that's there. So I guess the solution is that every time I draw anything, I will tell you over and over and over again, don't blend it this time, don't blend it this time, don't blend it this time. And if you don't do that, it goes wrong. Like, it's insane. So WebGPU sidesteps that by limiting how much, basically eliminating global scope. and limiting how much the scope of any particular like render pass or anything like that contains. So it's just going to be easier. It's going to be more capable. It's going to evolve better with hardware over time. And so, yeah, I think that you get 5 years down the road and basically nobody's going to be building new WebGL content anymore. Separately, we will almost certainly never turn off WebGL, because despite all the new content going, like if WebGL development stopped right now and everybody started building WebGPU, which would be insane because it's not released yet, will be soon, but we would still never turn off WebGL because there's so much existing content that makes use of it, and specifically existing content that has effectively been abandoned by its creators, not out of malice or anything like that. They just completed the project and moved on, and they're never going to go back and update it. And it would be a disservice on our end to say, hey, this swath of the internet, this interesting thread of content that people have built, it's gone now. It is the Flash problem. We are not Steve Jobs.
Yeah,
So
that sums it up for me. Thank you very much.
yes.
Oh, okay.
So I was wondering, since WebGPU is like an upgrade of WebGL, like if you work with the Chronos group, like just like what the collaboration was like, or if you kind of took it in different directions.
So yeah, I've worked directly with the Chronos group through WebGL. WebGPU, it's important to note, is not a Chronos API. It's actually developed under the banner of the W3C, which is where most of the rest of the web is developed. You were the one who asked about the shading language earlier. Yeah, the same answer applies here. Why are we not under Chronos? Legal issues, and I'm not going to talk about it. But like I've worked with both. I find that I like working with both organizations. They have different focuses. And for something that is a very web native API, I think that it is probably ultimately more appropriate for something like WebGPU to be developed under the banner of a web focused standards group. That said, like we have gained an awful lot from the connections that we've been able to have with the Chronos group through OpenGL. And the dirty secret behind it is that most of the people who are working on WebGL are now working on WebGPU, and we have all the same contacts. And so there's still a lot of collaboration that happens with people that operate through Chronos. There's some finicky like legalese limits about what work can take place where, and like what IP gets assigned to what. But in general, like this is true not just of this, but I found like the entire graphics industry and sort of the software industry in general. Once you get past the corporate CEO and marketing levels, everybody just wants to share the cool shit that they make. Like we're all so enthusiastic to talk to other people who work in the same area that we do, that the desire to share knowledge and share experience and techniques is super, super strong. And so everybody wants fundamentally to collaborate to enable everybody else to do their best. And the exact banner that you happen to be doing that under is largely a technicality.
So would you say that like you were effective in learning lessons from like Chronos and on OpenGL and WebGL, and like being able to transfer those lessons to the WebGPU? Because I think I've seen like some projects where some people don't learn the lessons that other companies.
Yeah, I mean, that's a fair way to put it. Like certainly we took, when developing WebGL, we relied a lot on the expertise of the people who had developed the APIs that they were based on, the GLES APIs. we, built up those APIs. We had a lot of cross-referencing with the different hardware vendors. Being able to fix bugs when you have like personal contacts at NVIDIA and stuff like that is much, much easier. And so that was very beneficial. Then going forward to something like WebGL or WebGPU, I knew I was going to screw those two up at some point. We carried forward all of the lessons that we had developed while building up WebGL. We also took a decade or more worth of experience seeing people use the API and seeing where people fell down and seeing where the bugs came out and seeing where the performance problems cropped up. And we took all of that into consideration as well. And so it's very fair to just look at it and say, like, this is an accumulation of knowledge from like the very start of when we began developing WebGL, and perhaps even all the way back to that original version of OpenGL in 1993. It's just we keep building on the lessons that we've learned from the generation before.
Oh, can I ask another question? Would we have are you building a WebAssembly
So yes, kind of. We have, so I mentioned earlier in passing, on the Chrome side, we have WebGPU, which is the thing that you access through the browser. We also have our own backend for that, which we call Dawn, and that's the actual implementation of the API over the top of Vulkan and V3D12 and Metal, and actually OpenGL, but that's a compatibility mode. We're not going to talk about it. When in developing that, we've also made headers for that native library available for compiling against something like WebGPU or WebAssembly. Too many web things. It's easy to get them all mixed up. We make those headers available for compiling against WebAssembly, and then we have a layer that we maintain that takes those calls into the native library and just redirects them through the JavaScript library when you are interacting with WebGPU or WebAssembly. Like I said, too much. Yes, that's about the only way you can do it. Now, actually, if you use WebGL in WebAssembly today, that goes through the exact same pattern. What will happen is you'll call something that looks like the native GL library, and it ends up just marshaling its call out through JavaScript and back through the WebGL front end.
there's like no performance benefit?
To the actual function calls, no. And in fact, there's a little bit of overhead. But if you are using WebAssembly to speed up your application, generally the expectation is that you're not doing that just to make like the API calls faster. You're doing it because you want to either A, take a large chunk of, like a large kernel of C++ code and run it as quickly as possible. Or B, you just have a large volume of native code and you want to expose it to the web in some way without recoding the entire thing. It can be more performant, but in a case like this, like simply making the draw calls, it's actually not going to be any different, or even maybe slightly worse because you have to keep jumping back and forth. So that's not the reason I would recommend using WebAssembly. You use WebAssembly because you want to code a much larger code base in a native language. Anyone else?
So you work on both WebGPU and WebXR. Do you think those will become interoperable, or are they already?
They are not already. It is my dearest desire that they become interoperable. I do not know exactly when that will happen. When it does, it'll probably be me doing the work, and I just haven't been given the time to do so yet.
Okay. So the students probably starting next week, they'll embark on what we call the final project. So these are month-long, 2 to 3 people, intense projects that do cutting-edge work. I think you may have seen last year we had 3 WebGPU projects. Wayne did one with his team, and then we had a couple of GLTF renders. So coming from 2021 into 2022, what would you recommend are like novel projects that can be built on WebGPU that can showcase the strengths of the API, help drive adoption of the API, and really showcase the students' work as well, that they have done some good work with WebGPU.
Oh, goodness.
But I'm definitely putting you on the spot, but feel free
You
to
are
email me
absolutely
on
putting
LinkedIn.
me on the spot. I don't know that I have a great answer for that right now. Like, definitely one of the things that you kind of gravitate towards is if there's things that you can do with compute shaders. That's an area where the web just hasn't seen people being able to use a GPU in that way, at least not easily yet. And so it's an easy way to stand out, to say, hey, look, I took this thing that you used to only have to do on the page, and now I can do it in a compute shader. Please don't like mine Bitcoins or anything, but yeah, I don't know. Look, it's hard for me to come up with like really unique things, because there's so many like creative usages that I've already seen online, and a lot of times it's just like they have to go through these heroic efforts to work around the limitations of the APIs that already exist, while trying to achieve at least some facility of some of the more modern techniques. And we're really hoping to just bring down the amount of hoop jumping that you need to do to access some of these more modern things. Yeah, I don't know.
So I guess to recap, anything with compute shaders is good, and then if the students have ideas, I'll certainly ask them to email you and maybe run it by you as well.
Yeah, sure. I mean, you can always reach out to me through email. I'm online on Twitter. There's in a previous slide, there is a matrix chat group that we have a link to here. This is where a lot of WebGPU developers hang out, and also a good chunk of the people who are actually implementing it in the browser and developing the spec. So if you want to get in touch with people who really know what they're talking about in terms of the API, that is a great place to be. Excuse me.
My next question is, what are some of your favorite projects, open source projects, that students can contribute to just in their free time?
Ooh, good question. So I have to give a shout out to 3JS. I'm friends with Ricardo, who maintains it. It's a really cool, ubiquitous project that has enabled many people to do interesting graphics work online. And it's really easy to contribute back to. Also, like, let me think. There are other graphics APIs like that, such as like Babylon or PlayCanvas. PlayCanvas, I think, is commercial, so maybe that's not an open source one, but Babylon is. Those are all great things to contribute to. There's a lot of like, there is a coworker of mine, Emmett Lilish, who maintains a web component called Model Viewer. It is like a single line library that, or you include the library, and then you can put a single line of DOM in your page that renders a full GLTF model. And it's a really cool project, and they're constantly evolving it and moving it forward. And that could be a fun place to see if there's any way that you can contribute. It is open source. You can get to it on GitHub.
GL Matrix.
Yeah, sure. I see where you're setting me up for. That's an area where, like, the library itself hasn't undergone a ton of maintenance recently, because I've just been too busy with everything else. But patches are welcome, and if anybody wants to help like maintain it and help like review patches that come in, then I wouldn't turn that down either. But that's kind of a heavy lift. So
My last question. I've always wondered this since following you on Twitter. I don't even know how many years ago. What's behind your username? What's the motivation behind it?
oh god, I was dumb in high school. Like that's about it. Like I was in high school and really into anime and everything, and a bunch of my friends all came up with Japanese sounding names, and the thing that cemented it for me was Gmail released as a service, and I immediately registered that as my Gmail address. And it's like, oh, well, I will never be able to get an address that concise again.
Yep.
So I guess this is just my username now, and it's very difficult to get rid of. So yeah, there's not too much more story to it behind that. Besides that,
Any other questions for Brandon? Okay.
you've all been fantastic for letting me just talk and talk and talk and talk. I hope I haven't bored you to death.
Brandon, thank you once again for sharing your thoughts and information about WebGPU with us. I'm excitedly looking forward to more WebGPU projects in the class, and I'll certainly send out invites to you to track their progress, and I'm sure the students will reach out as well.
Yeah, I mean the entire team that is working on these things loves to see people doing interesting things and doing projects with these APIs, and more so than that, we love hearing when things suck. Like when if you do something and you have a hard time with it, it doesn't run on your machine, or you find part of the API too difficult to work with, or anything like that. We like to hear about it because it means that we can make it better.
Yeah. Thank you once again, Brandon, for flying out, taking your time, and then sharing your ideas with us. Thanks.
Thank you.
So if you want to come up and chat with Brandon, you're welcome to do that as well. So
I'm going to stop
you can, and
the recording.